All right, guys, welcome to FRQ Type 4. We're going to talk about problems that I call graph-given questions. Now, there's really going to be two types of these, but in both cases you're given a graph. But what's different about them is how they're naming the graphs and the functions you'll be working with. But actually, they're almost identical in the way that you go about working with them. So let's start off with the one over here on the right. One way they'll do this is they'll give you the graph of a derivative, and then they'll ask you about the questions of the antiderivative. So all the questions will be circling around this one mostly, the function f itself. But an equivalent way that question could be asked is by giving you the graph of something they call f, and then defining a new function called g, which is the integral of f. Now the reason why these two questions are pretty much the same thing is because if this graph is the derivative of this, that means that the integral of that function is this one. So as you can see, this function here and this one, they're really kind of the same thing. They're both just one where you have a graph and its derivative above. It's just that in this case, the derivative of f is explicitly called f prime, and they don't give you this representation. Whereas over here, the derivative of g is f, and they do explicitly give you a formula. But all the rules are essentially the same. Okay, so it looks different in those two circumstances, but they're actually the same type of question. So what to expect? These are not usually calculator active questions. So they're usually things that you have to do without a calculator. So while you guys are practicing all these in your book, I would encourage you to try to do them without the calculator, because that's what they typically are. Okay, and in case you guys don't know, in the FRQ book, how can you tell if it's calculator active or not? Questions 1 and 2 are always calculator active. Questions 4 through 6 are always going to be non-calculator active. 3 is usually going to be calculator active, but it could switch. But 3 could be a calculator active question. So usually the first 3 questions are calculator active, and the last 3 are not. All right, but anyway, what are some common questions with these? Well, remember, they give you the graph of the derivative, and they might ask you to find the value of your function at a specific point, the value of the derivative at a specific point, or the value of the second derivative at a specific point. They may ask you to identify the relative extrema, and I just realized I need to be a little bit more specific, finding the relative extrema of f. So remember, they give you the graph of f prime, but a lot of times the questions they're asking are about f. So they're going to ask for the relative extrema of f, or the absolute extrema of f, or the intervals of increase and decrease of f, or the intervals of concavity and inflection of f. And then finally, I've noticed that they ask a lot of tangent line questions, which is a little bit repetitive. We talked about those a lot when we did our slope fields and differential equations FRQ, because those are popular there too. But I noticed they're actually quite popular on these questions as well. So without any further ado, let's go ahead and jump into some of our examples here. The graph of the function f shown above consists of a semicircle and 3 line segments. We're going to let g be given by this. So if this is g, then what I want you guys to understand, you don't need to write this necessarily, but the derivative of g, using the second fundamental theorem of calculus, we drop the integral and put that x inside, and we're left with f of x. Okay, so the derivative of g is what that graph is up there at the top. Something to keep in mind. All right, so first of all, let's go ahead and start off with g of 4. Okay, well, g of 4 is equal to the integral from -3 to 4 of f of x dx. Now what this means is this is the area under the curve from x equals -3 to +4. So we're going from here all the way up to here, and we want to find the area of all the pieces. So you could break this area up in a variety of ways, but here I've got a trapezoid. Here we have these little ramps that we talked about a while back. There's 2 of them. And then we have a right triangle here, and an equivalent right triangle right next to it. But notice how they're actually exactly the same shape, but one's above and one's below. So technically, we don't even need to worry about finding these two and adding them together. They're just going to cancel each other out anyway. So I really only need to bother with the green and the red sections up there. So let's go ahead and do that. So first of all, for the trapezoid, you are going to add the bases together. Now the bases are the parallel sides. So I have a base of 1 and a base of 2. So you add your bases together and you multiply that by the height, which is the side perpendicular to the bases. In this case, that would be 3. You divide that by 2. And so we have 3 times 3, which is 9 over 2, which is 4.5. And so there's that first area right there. That's going to be 4.5. Let's go ahead and we'll find the area of the red section, the little ramps. And as we talked about a while back, the area of a ramp can be found by finding the area of a square whose side lengths are the same as the side lengths of the ramp, and subtracting from that the area of a quarter circle whose radius is equal to those side lengths. So in this case, the side length is 1 of the ramp. The ramp is 1 space high and 1 space long, and so the square is 1 and the radius is 1. And so the area of the square is 1, and the area of the quarter circle is pi r squared over 4. So the area of this ramp comes out to be, if you simplify it, 1 minus pi over 4. Okay. Now since there's 2 of them, and you could tell they're identical, you might as well as just double it, which gives you 2 minus 2 pi over 4, which reduces to 2 minus pi over 2. And so that would be the entire red section added together. Okay. Now, this integral is going from -3 to +4. But like we said, since the orange triangle and the yellow triangle in the picture up here have the same area but opposite signs, they're just going to cancel each other out. So I'm just going to add together the green and the red. And so the green area was 4.5. And the green area was 2 minus pi over 2. And I'm not going to bother adding it together because it's an FRQ and we don't have to. So there you go. That'll work. All right, so that's how you find the value of the antiderivative. Now we want to talk about how do you find the next one, the g prime of 4. Well, as we mentioned before, g prime of x is just equal to f of x, right, by the second fundamental theorem of calculus. Therefore, g prime of 4 is equal to f of 4. In other words, what's the y value of the f function at x equals 4? Well, at x equals 4, the y value is -1. And we're all good there. All right, as for the last one, I want to find the second derivative. Now, if g prime of x equals f of x, then g double prime of x is equal to f prime of x. In other words, it's going to be the slope of our graph. The slope of our graph. The graph is f, so f prime would be the slope of our graph. So what is the slope of our graph when x equals 4? Well, luckily we're on a nice straight linear function, and it's pretty easy to find the slope of a linear function. All you have to do is find your rise and run, and you've got your slope. So it looks like I run 2 spaces to the right, and I go down 2 spaces. So my slope is rise over run, which is -1. Okay? So that's how we find the value of the antiderivative of an integral function and the derivative of an integral function and the second derivative of an integral function on a graph given type of function. All right, let's go ahead and move on to another type of example here. Find the absolute extrema, that would mean both the minimum and maximum of g of x, and justify your answer. So as you guys know, anytime you're looking for an absolute extrema, you're going to make a table where you have your input and your output that you're trying to maximize. So my input is x, and the output I'm trying to maximize is g. You always start with your beginning x value, which is -5. and you end with your final x value, which is 4. And then in between, you're going to find your critical values. And the critical values, once again, as we've said many times, are where the derivative of g, which is f, remember, equals 0. So where does the derivative of g, which is f, equal 0? Well, f equals 0 anytime it touches the x-axis. So those are all critical values. So I've got a critical value at -4. I've got another critical value at 1. And my last critical value is at 3. And so now what I need to do is I need to find g of -5, g of -4, g of 1, g of 3, and g of 4, and see which one comes out to be the absolute max and which one comes out to be the absolute min. All right, so let's go ahead and start with g of -5. G of -5 is equal to the integral from -3 is the bottom number, to -5. Now, it's a little bit hard to notice this, but you guys got to remember this, that anytime the number on top is smaller than the number on the bottom, we need to rewrite that. We need to flip it around, which we are allowed to do, but we have to remember to put a negative in the front when we do that. So that's kind of something that's not obvious, especially when we're dealing with negative numbers. It's a little confusing to notice, but remember, smaller number has to go on the bottom. Okay. Now, if you're working on a calculator with an equation, it doesn't matter. But when you're doing these area problems, you need to make sure you flip them yourself. All right. So let's go do this. So what this is asking for is what's the area from -5 to 3? And so that would be this little triangle right here. Or is it? -3. My bad. Okay, so that would be this little triangle plus this triangle. And once again, those look pretty identical to me. Don't they look the same? I think they're just going to cancel each other out. This one has a base of 1 and a height of 2, and that's a +2 area. And this one has a base of 1 and a height of 2. Oh, I forgot to cut it in half, didn't I? That would be actually an area of 1. Let me back up. And while I'm at it, I think I'll make it a green 2, or a green 1. So a +1, and the one on the bottom here is going to be an area of -1. So that area adds up to be a 0, and therefore we have negative on the outside, and the area is 0, and therefore the answer is 0. So we have an area of 0 at that point. Let's go ahead and continue. Now we want to do g of -4. So here we go, g of -4. So we start at -3, and then we go to -4. Okay, well, once again, we need to reverse those, don't we? So I'm going to flip that around, put the -4 here, the -3 here. So in that case, that's just the green triangle. If I'm going from -4 to -3, that's just the green triangle. And so that area is a +1, but because there's that negative in the front, it's going to become a -1. All right, let's go ahead and move on to the next one. And we're just going to keep doing that over and over again until we have them all. All right, as for the next one, we've already calculated the area of this trapezoid, right? And then we've also already calculated the area of this ramp. The area of the trapezoid was 4.5. And this ramp was 1 minus pi over 4, which means that this ramp was also 1 minus pi over 4. In our last problem, we just put them together. But in this case, we're going to keep them separate. All right, let's go ahead and read the question here. So I want to find g of 1. So here we go. G of 1 is going to be equal to the integral from -3 to 1. Now this time I don't have to flip them around and put a negative because now it's correct. The negative number is on the bottom, or the smaller number I should say is on the bottom. So we're going from -3 to 1. And so if I'm doing that, that would include the trapezoid and the first ramp. So I'm going to add together that purple area and that first ramp. So that's going to end up being 4.5 plus 1 is 5.5 minus pi over 4. Now I'm going to leave it like that for now, but we might have to get an estimate a little bit later. Let's go ahead and do g of 3. So if I'm going from -3 to +3, as you guys can see, I'm still going to do the trapezoid. I'm still going to do the ramp, but now I'm going to add the other ramp as well as this little triangle that's next to it. So this triangle here has a base and height of 1 cut in half is 0.5, and that's where we're going to stop. So now we're going to add together all 4 of these, 1, 2, 3, and 4. And so, gosh, that's going to be a lot. So we have 5, 6, 7 minus 7 minus pi over 2, if you added all those pieces together. And then finally, with our last one there, g of 4, you would just add the last little triangle, which is down here in the bottom, and that's a -0.5. Now, a shortcut, you guys, is just to know that so long as you're moving to the right, all you're going to do is you're just going to add that piece on to the last one you left off. So if I were to add a -0.5 to this, that's going to cause the 7 to decrease down to be 6.5. So you don't have to really do the entire problem again. That's only if you're moving to the right, you add the area. Now, if you're moving to the left ever, you actually add the opposite of the area, because that's what happens when you do the flip. But that can actually make things go a little bit faster if you just realize, okay, now I need to add this much, now I need to add this much. You just kind of keep adding it. You don't got to keep writing all of these over and over again. Matter of fact, on your FRQs, you don't have to show this at all. They really just want to see this for your work. Now, we're not done, though, because we need to identify what our absolute minimum is and what our absolute maximum is. Okay, well, I think the minimum is kind of obvious, thankfully. That would be this one right here. That's the minimum value. It's -1. What's the absolute maximum? It's kind of hard to tell with these weird pi fractions. Now, I know it's not 0. So my guess is probably going to be the 7 here. 7 minus pi over 2. 7 minus pi over 2 is definitely bigger than this one, right? Because this one's 0.5 less, so we know that's not it. I wouldn't cross it off on your FRQ, but we know that that's not it. The reason you don't want to cross it off is because they want to see that you actually got the numbers right. So leave it. But there's that. This one here, though, this number is smaller than this number, but this number is also smaller than this one, so we're subtracting less. But I think the fact that this one is actually 1.5 values less than this, and this one's barely just a hair less than that, I think that this one's still going to be the win. So my vote would say this is my absolute max. It'd be nice if you could use a calculator and just turn them into decimals and hope for the best. Or you could just try to fudge it, be like, okay, well, I'm just going to say that pi is basically 3. So 7 minus 3 is 4. Oh, I'm sorry, it's not 3. It's being cut in half, though, right? So 7 minus half of 3, or 7 minus 1.5, would be 5.5. Whereas this one is 5.5, and you're taking even more away from it. So obviously that one's going to be less. So our max would have to be that one. So you could also just estimate pi and figure it out that way. Whatever works for you. But there you go. And by the way, on the FRQ, you notice how I just crossed this stuff out? On your FRQ, if you cross something off, they don't grade it. That's why I said don't do this, because you want them to see what you got there. But if you don't want something included on your FRQ, cross it off. Don't take the time to erase it, because that takes time. But putting a big X through it's nice, easy, and quick. So just so you guys know, on the FRQ, if you just put a cross through something, then they're not going to grade it. Save yourself some time and don't bother rewriting it. And by the way, also on your FRQ, if you ever write something in the wrong spot, Circle it and draw an arrow to where it belongs. Don't erase it and rewrite it somewhere else. You don't have that kind of time to waste. And they will accept that. I've been told that by the College Board. Okay, now I'm switching gears here a little bit to the other type of graph given question. Remember I told you there was two types? Well, this is the other type. This is the type where I give you a graph of G prime and ask you questions about G, but as I told you guys, they're really pretty much the same question. You'll see that as we kind of work through some of these. But we are also going to be answering different things at this time. So let's go ahead and take a look. The function G is defined and differentiable on the closed interval from -7 to 5, and it satisfies this initial condition, which means that when x equals 0, G equals -5. The graph of y equals G prime consists of a semicircle, line segments in the figure above. So this is the derivative of G graphed here. We know an initial condition about G, and let's go ahead and continue and see what we can accomplish here. So example 3, identify each of the following and justify your answer. I want to find out where G is increasing, where G is decreasing, and where G has a relative extrema. Okay, so G is increasing when G prime is greater than 0. And where does this happen? Well, it happens anytime the derivative is positive, and that's anytime the derivative graph is above the x-axis. So that would be here and here. Now, to be safe, I would like to make the semicircle a separate interval from the triangle. And the reason for that is because right here where they connect, it's actually on the x-axis. And at that point, the derivative is not positive. And since it's not positive there, technically G is not increasing there either. But I've seen sometimes on the AP test, they just kind of just put it all together as 1. So here's how I think is the best way to write your answer: from -2 to +2, and from 2 to 3, 4, 5, 5. But technically, I think it might be okay to do this. Just put them together as one big interval. I would not personally, but I've seen it done. I just don't like it. Okay, the next one, number 2. G is decreasing. You guys got this by now, I'm sure. When what? G prime is less than 0. And this happens anytime our graph is below the x-axis, which happens on the following intervals. So that would be from -7 up to -2, and then from here to here. Now, that's an issue because where it's touching the x-axis is not clearly defined. So I'm going to show you what you can do here with that situation. But let's do the left side. The left side's easy. We're going from -7 to -2. That's my first interval. Now what you can do if you're really short on time is just go ahead and take a guess, right? And then maybe put a star next to it and come back to it later. But I would guess that that's probably going to be 4.5 because it's halfway between 4 and 5. And then it ends at 5. That would be my guess. Now, there's a way you can actually solve it. It's a little bit challenging. It requires you to have some expertise with some algebra. I think maybe the easiest way is just to look at the slope. Okay. Now, what is my slope? Well, if I'm going from a +3 to a +5, and a y value of 3, -1, just calculate the slope, y2 minus y1 over x2 minus x1. So you get -4/2, which is -2. Okay, so let's see if that helps us at all. So if my slope is -2, that means I'm going down 2 over 1. So I'm at 3. So if I go down 2 and over 1, that's going to put me right here at the following point. That would be down 2 oops, did that wrong, sorry. Down 2 over 1. So now I'm at 4, 1. And the next time I go down, it's going to skip the point that I care about, but we can get kind of nifty about this. I can go down only one space and over how far. So if I go down blank over, well actually I'm going down 1 and over blank, what would that blank have to be? Negative 2 over 1 is the same thing as 1 over what? Well, if you cross multiply, I guess you can kind of find it. 2 times, we'll call that x, 2x equals 1, and so x would equal 1/2. So that would mean x is going to be a half. It says negative half, and that's just because our slope was negative. But it does, in fact, go over a half. Another way you could do it is you could actually find the equation of this line using our point slope formula that we've learned earlier this year. Just find the slope, plug in x and y, you found the equation of the line, and then you can go ahead and plug in the y value, which is 0 for the point that you're looking at, and you can solve for x to figure out what the x value is. So there's a few ways to get exact, but as you can see, that takes a lot of time. And so I would just hedge my bets and think, okay, I don't have a lot of time. I'm going to guess that that's probably 4.5. Then I'd put a star next to it and think, okay, and if I got some time left, which may happen, I'll just go back and do that one again, just to check it, see if I can figure it out. But there you guys go. Now the next question is, where are the relative extrema? Number 3. So we would say G has a relative max when G prime goes from positive to negative. This happens at what places? Well, if G prime is going from positive to negative, that's going to happen anywhere where the graph goes from being above the x-axis to below, and there's only one place where that happens, and it's right there. To the left, it was above, and then after that, it was below. And so, once again, I would have to star that if I wasn't sure of my answer being 4.5, but it is 4.5. But there you go. That's where it changes from positive to negative. And contrary-wise, G has a relative minimum when G prime goes from negative to positive, and this happens at right here. So that would be negative 2. There are no other relative extrema up there. All right? So that takes care of that type of stuff that you may be asked. Let's move on to the next one here. Example 4. Pretty similar type of question, but now we're talking about concavity. And when you're talking about concavity, that's a second derivative thing. Okay? So here we go. Number 1. G is concave up when G double prime is positive or greater than 0, right? So, but where is G double prime on this graph? Well, if this is a graph of G prime, G double prime is the slope of the graph. So G double prime is the slope of G prime. So if I'm looking for where G double prime is positive, that means I'm looking for anywhere on this graph that I'm looking at right now. I'm looking for where it's increasing, moving in an upward direction, which is here. G prime is going in an upward direction, and here G prime is going in an upward direction, and here G prime is going in an upward direction. And so I would say this happens on -7 to -2 and -2 to 0 and 2 to 3. All right, next one. G is concave down when g double prime is less than 0. And this happens on what? Well, since g double prime is a slope of g double prime is negative anytime g prime has a negative slope. And that happens here and here. So that would be from 0 to 2, as well as from 3 to 5. Now, let's make some space here. The next question is, where is G concave up? I'm sorry, where does G have points of inflection? Before I answer that, I'm going to highlight some things really quick, just so we don't forget what the colors represent. Pink means concave up, green means concave down. All right, so G has a point of inflection anytime. Now, a lot of times in this class, I've written POI. I wouldn't do that on your FRQs. I would just write it out. I know it's a little bit longer, but when you actually take your test, don't assume that they know what you mean by POI. G has a point of inflection when G double prime changes signs. And this happens when? Well, basically, when the slope changes. So like here, we go from pink to green. Here we go from pink to green. And here we go from pink to green. And so that would be at x equals 0, x equals 2, and x equals 3. So those are official points of inflection. All right, let's go ahead and take a look at number 4. Sometimes they'll ask a question like this where they'll say, not only do I want to know where it's concave up, but I also want to know where it's decreasing. So G is concave up when G double prime is positive, which we've already said, and is decreasing. Now this takes us back to the last slide. G is decreasing when the first derivative is less than 0. So on our last slide, G double prime is less than 0 anytime it's below the x-axis. And so that would be here and here. So I want to know when G is concave up. So I'm looking for pink. But I also want to know where it's at the same time decreasing, which is orange. Where is it pink and orange? Well, here is where it's pink and orange. So this happens on -7 and -2. Okay, so those are the types of concavity and points of inflection questions that you might be asked. And let's take a look at number 5. This is the tangent question. I've seen quite a few of these on these graph giving questions, so I thought, well, hey, let's go ahead and do it. It can't be too bad. All right, so in this case, what they're doing is they're giving you a whole new function. You know, we know about this function called G, and just a second here, might need to make a little change. I just realized the numbers were kind of different there, so I changed this to 0 and this to 0, but it should be fine on your guys' worksheet. Okay, so like I was saying, they give you a function where, you know, we're used to the g function and the g prime, but now they've created this whole other one. Sometimes they'll do that, and that's okay. They want us to find the equation of a line tangent to h. Well, how do you find a tangent line? Well, as you guys know, we need to find a slope, and that can be done by finding the derivative of h and plugging in the x value they give us. Next, we need to find the x value of h, which they've already given you, so that's 0. And then you also need to find your y value, which you can get by plugging 0 into your h function. Okay, so we need to do those 3 things. So we have x, nice. Let's move on to the y. Let's do y first. So h of 0 is going to be equal to g of 0 minus 1/2 times x squared. I'm sorry, not x squared. It's going to be 0 squared. We're plugging in 0. Okay, so now in this case, that just goes away. So that means that h of 0 is equal to g of 0. And g of 0, according to the instructions, is -5. That's nice. Now, technically, they could be mean, and they could give you, they could ask you to find the line tangent to the graph at a different point that's not the one they gave you, in which case you would have to do an integral to find area under the curve to find it out. You would have to say, okay, if I want to find g of 1, for instance, you would have to say, okay, fine. So that would be g of 0 plus the integral from 0 to 1 of g of x. You have to have your, or g prime of x. You would have to have your starting point plus the area under the curve from that starting to that point that you actually want, right? In this case, though, they don't want that, so I'm just giving you extra information. But anyway, h of 0 is -5. So we've got our y value. It's -5. We've got our x value. Now we need to find our slope, which is h prime of 0. So first of all, then we've got to find h prime, which means it's going to be g prime minus, and if I take the derivative of that, I'm going to end up with just x. So then h prime of 0 is equal to g prime of 0 minus x. All right. Now g prime of 0, that's just going to be the y value of our graph, because we have a graph of g prime. And when x equals 0, what's the y value? Well, it looks like it would probably be about 2. And then we need to plug 0 in here. And so h prime of 0 is equal to 2. So now I've got my slope, I've got my x, I've got my y. We're ready to write our tangent line. So we have y equals the slope times x minus x1 plus a -5. And since it's an FRQ, I would just leave it like that unless they ask for more. We're good to go. All right. And so that'll end that one. And I believe that was our last question that we'll go over for this. So hopefully that was helpful, and we'll see you guys later.